Okay, so a few more examples here. Example 6 goes back to this, let's just read it. A city has the following tax code. The first $20,000 of income is tax-free. The next $30,000 is taxed at 5%. And any other additional income is taxed at 8%. And if X is a taxpayer's income, write his or her tax as a function of X. So, obviously, we're going to have three different cases. Whether the income is less than $20,000 or between $20,000 and $50,000 or above $50,000. Okay, and this is what we need a piecewise defined function for. So if we have if t of x is the tax for someone with an income of x, what would that be? Well, we have to write our cases first over here. So we have one case where if x is between 0 and 20,000. Another if x is between 20,000 and 50,000. And another if x is bigger than 50,000. And we're going to see it probably doesn't matter. We should probably include these. Do we make these inclusive inequalities? I'm going to do that right here. Okay. And then we wouldn't include this because we don't want to use two different rules, but we'll include this for here. Okay. So now we've arranged it so that any value of x is going to fall in exactly one of these three cases. And so in the first case, if x is between 0 and 20,000, of course the tax is going to be 0. All right, now if 20,000, if x is in this range, remember the first 20,000 was fixed, it was tax-free. The only thing that's being taxed is the income after 20,000. So we're going to have, it's not x, but x minus 20,000. Okay, and that's being taxed at a rate of 5%. Okay. All right, and we can know that this will be a positive number because x is in this range. All right, then, well, what happens if x is bigger than 50,000? Well, that middle 30,000 is still being taxed at 5%. Okay, so this taxpayer will have to pay tax on that. So that'll be 0.05 times 30,000, and then plus 8% of whatever is left. So that would be x minus 50,000 times 0.08. Right? And we would, you could simplify this, but that's all there is to that this problem. Okay. For example 7, we have a closed box with a square base and has volume of 100 cubic centimeters. If x is the length of the side of the base, write the surface area as a function of x. Okay, so we have this. We know that we sort of need to know the formula for the surface area and the volume. For the volume, the volume is length times width times height, but in this case the length and the width are both the same. They're both equal to x. And we can call this height, we can just call that h if we want. And then the volume is going to be x squared times h. But we're given that the volume is 100 centimeters, or cubic centimeters. So we get 100 is equal to x squared times h. Now at the same time we have the surface, we figure out what the surface area is. What will that be? Well, there are going to be 6 sides altogether. We include the top because it's closed. And the area of the top and the bottom will be x times x. That's x squared. So it's going to be x squared plus x squared. That's 2x squared. And then these 4 sides, the area of each side is this rectangle. The area is x times h. So this is going to be 4 times xh, right? So that's the surface area. What are we trying to do? We're trying to write the surface area as a function of x. So that means we just have to replace this h with something in terms of x. And that's where this condition comes in. Okay, so h, to solve for h, we can just divide both sides by x squared. And switch things around, and we get h is going to be 100 divided by x squared. So then we can just substitute that in here. So the surface area is going to be 2x squared plus 4x times 100 over x squared. And if we wanted to simplify this, this would be 2x squared plus 400 over x, because this x and one of these x's will cancel. The last one is probably the trickiest one. We have a conical tank that's 10 feet tall with a radius of 3 feet. As shown, write the volume of water in the tank as a function of the water level h. Now hopefully you can see that in this picture we actually have 2 cones. Okay, we have the tank and then we have the body of water, the cone of water. And this is what's changing, and this is basically we're asked to find what's the volume of this inside cone, this water cone. We remember that the volume of a cone is 1/3 pi r squared times h. Okay, if you remember that. If you don't worry. That formula will be given to you if you need it. Where r, of course, is going to be this radius, the radius of the water cone. Now, so once again, we want to write this r, replace r with something in terms of h. So how do we do this? Well, there's a little trick here, so that in addition to seeing 2 cones, we should see 2 triangles here, 2 similar triangles. Okay, a big one where this length is 3, this length is 10, and then this length is r, and this length is h. So by similar triangles, I say it as I go, this is to this as this is to this. So 3 is to 10 as r is to h. And then this gives us our relation between r and h. We can cross multiply, we get 3h equals 10r. And what are we trying to do again? We want everything in terms of h. So we want to write r equals something times h, so we divide by 10, and we get r is going to be 3/10 times h. Okay, and then we can go ahead and plug this back into here. So the volume will be 1/3 pi 3/10 h squared times h. And if we clean this up, this will be 1/3 pi times 9 over 100. So this will be, well, just say this is pi over 3. times 9 over 100 times h cubed, and I think we can cross out one of these 3's, and so we'll get 3 pi over 100 times h cubed, I think. Okay, so that would be the volume as a function of h.